Okay, so in this video we're going to look at mass spectrum. We're going to look at specifically linking it to section 1.5 in your specification. We're going to look at actually how mass spec works, so what the different parts of mass spec are. Once we've looked at how it works, we're going to look at how we can use mass spec to calculate the relative formula mass for a compound and the relative atomic mass for an element, looking at different isotopes and combining those isotopes together to work out what the different what the relative atomic mass actually is. Okay, and then looking at from our mass spec how it can be used both in athletics, in the identification of banned steroids, but also in pharmacy and pharmaceuticals, in the identity of drug precursors. Okay, so if we go on and look at what actually happens in a mass spec and how it actually works, okay, we can see we've got different stages. Okay, so we start off with our sample here. Okay, that sample is passed into a heater, and the heater vaporizes the sample. Okay, so we're ending up at this stage, we're making a gas. Okay, the gas is then bombarded with a beam of electrons to turn my gas into a positively charged ion. Okay, and that positively charged ion is then accelerated through our slits. Okay, and when we then go and pass it through a magnet, okay, that magnet obviously deflects my charged ion. Okay, and different ions get deflected by different amounts. Okay, so what affects how it gets deflected is the mass to charge ratio. Okay, where Z is charge, and obviously M is the mass. Okay, so the biggest the mass to charge ratio, the less it's deflected. That makes sense because it's heavier. Okay, so the heaviest ones get deflected the least, and then the least heavy ones get deflected the most. Okay, and then we can use this to calculate what the relative formula mass of a compound might be. Okay, so if we look at what an example mass spec actually looks like, okay, and this is one for pentane, so we're starting off with C5H12. Okay, we can look at calculating what the relative formula mass of the compound is, and the way we do that is look at the biggest peak. Okay, so that one has a mass to charge ratio of 72. Okay, so I know that my mass to charge ratio is 72. I know that my charge is equal to 1 plus. Okay, so therefore my mass must be equal to 72, just by rearranging that equation. So I've got mass is equal to 72 times Z, and Z is equal to 1. So mass is equal to 72 times 1. Okay, and this links in to your specification point B, where it's talking about measuring the relative molecular mass of a compound. So in this example, we've got pentane. We could look at different compounds, and we use exactly the same principle to work out what the mass of that compound was. Okay, we can also then look at the other peaks. Okay, so I've got a second peak there at 57. Okay, so that's my peak at 57. Okay, so I've got a jump of 72 to 57. I know that jump is worth 15. Okay, so I've started off with, let me just rub some of the things that I don't need anymore off. Okay, so I've started off with a mass to charge ratio of 72. Okay, and I've lost 15, so I can then work out what has been fragmented off, and therefore what I have left. Okay, and this can help me with what the identity of the compound is actually going to look like, and this will help me as well when we look at spectroscopy in more detail in Unit 2. Okay, so I know I've lost 15, and I know 15 is worth CH3. Okay, so I started off with C5H12. I've lost a CH3, so I end up with C4H9. So I know that that fragment is due to C4H9, and I could do exactly the same for each jump and work out what I'm left with. Okay, and that could help me work out if the molecule was branched or unbranched. Okay, so in this example, I know my longest chain is C5H12. I know I've also got a fragment of CH3, and I've also got other fragments, so I would know that this is going to be an unbranched chain. Okay, so this would help me identify if I've got a branched or an unbranched isomer. Okay, we can also use mass spec to actually work out the relative atomic mass of an element. So this one is looking at boron. Okay, so we need to work out what the actual RAM of boron is, the relative atomic mass of boron is. Okay, and the way I work it out is I look at what the isotopic mass of my isotope is. Okay, and I multiply that by the abundance. And I do that for both isotopes. Okay, so isotope B times abundance. Okay, and then whatever I work out what that sum is, and whatever I get as an answer, I need to divide by the total number of particles. Okay, and that's my general way of working out what my relative atomic mass is. Okay, so if I look at this example, I know I've got an isotope at a mass to charge ratio of 10, and I've got a second isotope at a mass to charge ratio of 11. Okay, I know that my isotope at mass to charge ratio of 10 has an abundance of about 23, and I know my isotope at mass to charge ratio of 11 has an abundance of about 100. So I know my relative atomic mass is equal to my isotope 10 times its relative abundance plus my, let me just delete this bit out so you don't get confused. Okay, plus my relative abundance at 11 divided by the total number of particles, which is 100 plus 23, which is the same as 123. Okay, that bit gives me an answer of 230. That bit gives me an answer of 1100. That gives you a total answer of 1330. Okay, and to get 1330 divided by 123 is equal to 10.81. Okay, I'm going to leave it as 10.8 to 3 significant figures. Okay, so my relative atomic mass of boron is 10.8. And I could do that exactly the same for any molecule. Obviously, for diatomic molecules, I'm going to end up with a more complicated fragmentation pattern. Okay, so we can see, and then we can look at my accelerator and my mass spec rather again. Okay, and we can see how this is going to be used to actually help in the detection of steroids in athletes. Okay, and how it's going to be used by pharmaceutical companies in terms of identifying drug precursors. Okay, so if we first of all look at the athletes, I can run my sample, okay, and if I had any steroids present, okay, I would have it in the urine. The urine would be vaporized. Okay, my steroid would be bombarded with electrons as normal, okay, with my electron gun. Okay, and then my with my electron gun, and then accelerated through the accelerator, deflected through the deflector. Okay, and then I'd get it detected, and I'd get some sort of fragmentation pattern. Okay, I could then compare my sample fragment with an actual fragment of a banned steroid, okay, which I'd know what that would look like. Okay, and obviously if they're similar, which in this case we're saying they are, or if they're the same in fact, and which in this case we're saying they are, I would know, I would have conclusive proof that my athlete had cheated and deserved to be banned because he'd taken a sample of steroid which he wasn't allowed to use. Okay, and we could have exactly the same principle in synthesis of drug precursors, where again we'd know what the sample that I had made, what the spectrum looked like. Okay, and we'd know what the actual drug looked like from the mass spectrum we would expect, and again we could prove that we'd actually made the drug that we wanted to. Obviously, in an industrial scale, this is advantageous because the amount of drug that you need for a mass spec is very small, so you're not wasting loads of your expensive material, okay, to identify the product that you're actually wanting to make, to prove that you've actually made what you wanted to make. Okay, so we can look at, in terms of mass spec, for our topic 1.5. Okay, we can look at how it works. So we've got vaporization of the sample. We've got then, once it's vaporized, ionization of the sample. Once it's ionized, acceleration of the sample. Once it's accelerated, deflecting using a massive magnet. Okay, and then depending on the mass to charge ratio, it's going to deflect by different amounts, and you're going to get your spectrum that you actually see on the detector. Okay, we've looked at how we can use a mass spec to see what the relative formula mass and the fragmentation pattern of a compound is. Okay, we've looked at how we can use mass spec to see what the relative atomic mass of an element is. Okay, and we've looked at mass spec to see its uses, both in terms of identifying banned steroids in athletics, okay, and also in identifying drug precursors in pharmaceuticals. Okay, and this is what you guys need to be able to explain when you're looking at your 1.5 section. And with next video, we'll look at an example past paper question, and we'll have a go at creating a model answer for that.